Welcome back. In this lecture, we will look at certain qualitative features on selection rules. Even though this is presented in the context of beta decay, the ideas that are presented here have wider applicability. So, what is the critical physical basis for selection rules? You might have heard selection rules in the context of a variety of spectroscopy. So the central aspect here is that photon has an inherent spin. Spin of a photon, S is equal to 1. And because spin is a form of angular momentum, this has to be conserved when photon is taken up by the system or photon is emitted by the system. So conservation of angular momentum is the central physical aspect that provides the constraints of selection rules in a variety of spectroscopies. So mathematically, how the selection rules are obtained is via certain integrals. So the integrals will involve two wave functions. One is the initial wave function, another will be the final wave function. And this quantity, so it might differ from a spectroscopy to spectroscopy. In this case, it is the transition dipole moment. So that involve certain amount of quantum mechanics, and the basis for this expression is via quantum mechanics, how the wave function changes when it is perturbed by an, let's say, an external electromagnetic field and so on. Okay, so you have to take some courses in quantum mechanics to make sense of this expression, but typically what we mean by selection rule is that if this integral is non-zero, that means it's an allowed transition. If this overall integral is zero, then the transition is not uh, allowed. Okay, so this provides certain kinds of constraints and an insight into the nature of the system that you have. Okay, so what is a kind of typical experiment? Let's say you perturb the system via an external electromagnetic field and the system changes its energy. Okay, so we ask the question whether the system can take up a photon and so on. Okay, so let's move on. So your first exposure to selection rules might be via chemical spectroscopy. Here, the electrons are the ones that typically which are changing its energy, or there are different modes within the molecule wherein energy can be stored. So it can be the vibrational mode or the rotational mode, or the electrons themselves can change the state. So the question you ask is typically when they're exposed to certain perturbations, can the vibrational modes or the rotational modes or the electron themselves can take up energy? That's the question we ask. In nuclear spectroscopy, the nucleus is what will take up energy. The different degrees of freedom available within the nucleus can change, and we ask the constraints within which these changes are possible. So there are two ways of looking at selection rules. One is that there are, let's say, gross selection rules. Okay, so again, these are applicable to nuclear spectroscopy, atomic spectroscopy, molecular spectroscopy, and so on. So you ask a question, under what conditions would a specific transition occur? For example, if you want to ask a question whether via taking up a photon would the rotational degrees of freedom would they change with the energy stored in the rotational degrees of freedom? What this specifies is the rotational transition, whether I can go from one rotational uh, uh, state to another rotational state. To answer this question, when you go through the quantum mechanics, you would see that the molecule has to be polar. So, let's say you have a Raman spectroscopy. So, here the polarizability should change uh, during vibration. Under these conditions, the molecule will be Raman active. So you can come up with different conditions uh, which provides an insight in not only into the nature of the system, and it also tells you when you have a photon of a particular wavelength, into which degree of freedom that energy is taken up into. This is one way of looking at it. And there is also specific selection rules. So here, the constraints are provided via quantum numbers or certain symmetry states of the molecule of the system. Okay. So, for example, if you consider the electrical dipole mechanism for transition, you can come up with certain constraints. If the atomic transition involves a change in the angular momentum of the electron, if the change is plus or minus one, then it is an allowed transition via this mechanism. Or if the overall angular momentum changes in a particular manner, uh, if the spin angular momentum changes in a particular manner, if J is the combination of the orbital angular momentum and the spin angular momentum. So these kinds of constraints are very useful to know whether these energy transition is possible when the system is exposed to a photon of a particular energy. So you can have constraints in infrared spectroscopy, Raman spectroscopy, and so on. Likewise, in whether rotational transitions in microwave spectroscopy, and so on. So these are you have to have taken some classes in quantum chemistry to make sense of these symbols, as well as how these constraints are obtained. Okay, so these are Garade and Ungarade. So these are indicative of the symmetry states of the wave function and so on. Okay, so overall, this one way of looking at selection rules. This is a more specific way of looking at selection rules. So you would also, in a related context, you will have heard uh, about space quantization. This sort of not an obvious terminology. We'll look at why this terminology came about. Again, this has to do with angular momentum. So specifically with respect to angular momentum quantization. So this was first brought about in a dramatic manner via this Stern-Gerlach experiment. In many courses in quantum mechanics, this is an introductory experiment because the mathematics of the system is rather simple. And the quantization principles can be illustrated very well using this system. So an introduction is provided in this wiki link. So what is the system? What is the experiment we are looking at? You have a silver atom, that's the collimated beam of silver atom, which passes through an inhomogeneous magnetic field. There are reasons why this system is designed in this manner, why we have inhomogeneous magnetic field and so on. We won't go into this in this lecture, but you can look at this wiki link or some course in quantum mechanics who would have already elaborated why this experimental system is so arranged. So what is that we have? So when there is a particular reason why silver atoms are susceptible or ideal for this experiment, when collimated silver atoms pass through this, they segregate into two particular spots. Okay. So in a way that this space is not occupied. Only two spots in the screen is occupied. Okay. So this is what we mean by space quantization. Okay. So because the all the space is not uniformly accessed, but only certain parts of space is accessed, which leads to the terminology space quantization. We will look at some more details in the next lecture. This is extremely good um, visualization of what's going on. So we would just look at this visualization. You can also look at it. I'm providing the reference for this. So what the Stern-Gerlach experiment provided was that there is an internal degree of freedom. Okay, so there is a specific reason why silver is ideal for this experiment because of its electronic configuration, um, and why its angular momentum, that is the orbital angular momentum and the spin angular momentum, is ideal for illustrating this experiment. Okay, so it provided an insight into this internal degree of freedom called the spin quantum number or the spin angular momentum, which can only take up two values. So once you have an angular momentum of a charged object will have a current. So, and hence it will have magnetic dipole, and this magnetic dipole will respond to external magnetic field. In this case, because the magnetic dipole can take two values, it segregates into two spots in the screen. So you can go through this self-explanatory video and probably go through this link to get an idea of what we mean by space quantization and how it is related to spin angular momentum. So there are two kinds of angular momentum. One is the orbital angular momentum and spin angular momentum. Both have to be conserved in many cases. Okay, so we have already seen some of these expressions in previous lectures. So this is the angular momentum quantum number. This is the overall angular momentum. So if the angular momentum quantum number has a particular value, let's say in this case, L is equal to 2, not all components of the angular momentum can be completely specified. Because we are constrained by the uncertainty principle. In the most common case wherein you have seen uncertainty principle is the constraint between linear momentum and linear position. Likewise, there is a constraint between angular momentum and angular position. These constraints the implications of this constraint is that only one component of the angular momentum, which we take to be the projection of the angular momentum along the z-axis, only one component can be completely specified, and the other two components, that is the x component and the y component, cannot be specified. Again, if you're not clear about this, you should take up some course in quantum chemistry wherein these things are clearly presented. But for this, the scope of this class, just a qualitative understanding of these principles is sufficient. So the z component of the angular momentum can take up certain specific values. Not all possible values are obtainable. Only specific values are obtainable. That's why you say that the z component is also quantized. It can take up m sub l to be 1, 2, 1, 0, minus 1, and minus 2. So all these things are connected to what you've seen from your high school, right? That is the d orbital has L equal to 2, and it can take 5 possible d orbital structures, right? So all these, and each of this orbital has certain angular momentum along the z-axis. So that is what is shown here. So because spin quantum number can take two particular values, and spin is also a form of angular momentum, it can combine with the orbital angular momentum in a vectorial sense. These can add up and give rise to the total angular momentum of the system, and that is indicated by the J quantum number. They will also take up certain values. That is the projection of the J quantum number along the z-axis can also take up certain values. In the absence of external magnetic field, all the angular momentum states, okay, the different MJ states have the same energy. However, when you expose the system to an external magnetic field, the magnetic moment is different for each of these systems. Therefore, the energy of each of this level is different. Therefore, the system splits. There is a degeneracy which is opened up because of the exposure of the system to external magnetic field. Okay, so that's what I meant by resolving the angular momentum. That you know that there are different angular momentum states. It is only possible to know when you expose the system to external magnetic field. Again, I've provided some links which provide additional information in case you're already not familiar with all these notions. So in the next lecture, we will take up another important feature. It is a great truth of reality. This was brought out in the context of beta-decay. So this is a slightly advanced topic, but this is to just perk your curiosity on the nature of reality. So that will be taken up in the next lecture. Thank you.